Okay, so we have once again come back to field theory. So let's start by recalling what we have been doing here and what we have done so far. We started our discussion with a field f, any field, and say a non-constant polynomial fx is given over f. That means fx is a non-constant element of the polynomial ring fx. Then we have already proved that there exists an extension E of the field f with these two properties. The first one is that you can factorize fx over E as a product of linear factors for some positive integer n, and over E means of course that this C and all the AIs are coming from the extension E. And the second thing is that the degree of this extension E over f is minimal. Now, given a polynomial, if you cannot factorize the polynomial over the original field, you then try to enlarge the field by adding more stuff. So these things, these AIs, if they are not originally in the field f, you then create an extension of f in which these things are there, so that a complete factorization is possible. So that means considering a large field allows you to have a factorization like this. So that means you on the one hand you have to enlarge the field, but to control this at the same time we have this second condition also, that okay, we are going to take a large field but only large enough so that we have this factorization and not more than that, and that is why we need this degree to be minimal. Now such an extension has already been called a splitting field of the polynomial. So this E is a splitting field of fx. Over E, fx splits completely. But then, as we saw previously, the natural question arises that okay, if there is one splitting field, maybe there are others also. Is there any relationship between two splitting fields of the same polynomial? So we already discussed something about that, and we in fact obtained one result in this direction, a very small result. So this is how we next proceeded. Let, from our proof of the fact that splitting field exists for a polynomial, we somehow came to the conclusion that we need to look at quotient rings of polynomial rings by principal ideals generated by some polynomial, and we need to look at relationships between two such quotient rings. So we are now heading in that direction, and on the way to that thing, that relationship, we have already obtained this thing. Let f and f prime be fields, and let tau from f to f prime, these are isomorphic fields, be an isomorphism of f onto f prime. For the sake of notational simplicity, we have also devised this notation for So these are things we have already seen, we are just simply recalling. For every alpha in F, we write alpha prime to mean the image of alpha under tau. Then the map tau star from the polynomial ring Fx to the polynomial ring F prime T given by this formula alpha naught x to the power n plus alpha 1 n minus 1 etc. plus alpha n minus 1 x plus alpha n. So this is any polynomial in x over f, that means an element in this polynomial ring. Its image under tau star has been defined to be this. Notice the primes here, that means we are applying the original function tau on these coefficients, these field elements. T plus alpha n prime. Okay, then this map is an isomorphism of the ring Fx onto the ring F prime T such that alpha tau star is equal to alpha prime for every alpha belonging to F. This is what we proved in the previous field theory video. Okay, so already we have an isomorphism, a ring isomorphism between this polynomial ring and this polynomial ring, which behaves exactly like how tau itself behaves, means what we have decided to call here. Just like tau, on the field elements, tau star has the same behavior. Now we are going to take things further. We are next going to consider this type of quotients, okay, which will ultimately be helpful in our proof of the fact that two splitting fields in fact are isomorphic by an isomorphism that keeps the underlying field. We have already discussed about it, right? Say you have a polynomial fx for which you have found two splitting fields, say E1 and E2. Our ultimate goal is to prove that there exists a field isomorphism from E1 to E2 such that if you restrict that isomorphism to F, because E1 and E2 are both extensions of F, so they both contain F inside of them. If you restrict this isomorphism to F, then you get the identity map on F. So now we see the next step in that direction, and that thing is this. Oh, and the statement that this tau star is an isomorphism which behaves like this is your lemma 533. Now next we have this lemma 534. So the statement of this next lemma is this: there is an isomorphism there is something else I forgot to mention here. I will mention it. Let me first write the statement. There is an isomorphism tau star star of this quotient ring fx by the principal ideal generated by the polynomial fx, of course, which is coming from here, this principal ideal, onto this quotient ring. Such an isomorphism exists such that alpha tau star star is equal to alpha prime. So you see that we are going step by step, right? First we had tau, which is an isomorphism between the fields f and f prime. Then we moved to the polynomial rings over those fields, and there we again got an isomorphism tau star, which behaves like tau here. I mean, its behavior on the field elements are identical. Identical means similar, and then still we take one more step where we are now considering quotient rings of those polynomial rings. There also is an isomorphism between two such structures, again which behaves like this on the field elements. For every alpha belonging to f, and there is something else also. And this may look quite complicated, but we will decipher everything slowly. This is equal to t plus f prime t. Now before we start the proof, let me now mention the thing that I was saying I forgot to mention here. You see, in this, you already see what this isomorphism tau star is. Actually what tau star does is this: you are given a polynomial in your domain polynomial ring fx. Its image under tau star is just an exactly similar polynomial in the new indeterminate t. Previous indeterminate was x, now in place of x you have t, and the coefficients themselves are being replaced with their images under that first function tau. Okay, so this according to these primes, its definition, for example, alpha naught prime is nothing but the image of alpha naught under tau. So that's why these things are elements in this isomorphic field f prime. So this becomes a polynomial in f prime t. Okay, now the thing that I forgot to mention here is this: if you don't use this actual expression for a polynomial and instead you decide to write say you give this polynomial a name, the input polynomial. Say you call it fx. Fx is this. Then its tau star image, you already know what it is. This is the definition, but we are denoting that image by f prime t. Okay, so f prime t is defined to be equal to this. This is somewhat like calling alpha tau alpha prime with a, for the previous function tau. Here also calling fx tau star f prime t. It's just a name given to the image, because you need to again and again mention it, right, when we are proving this. So it's just a name. And do not think that I already said something about this in the previous video also. Do not interpret this f prime t as the derivative of the polynomial f of t. Okay, that the derivatives don't make any appearance here. Okay, so and that f prime t is this f prime t. So now we prove this. Note that this statement actually does not have the definition of tau star star. We have to define it. So we will do that first, and then we will go through the usual steps. So proof. We define from fx by f of x to f prime t by f prime t. If you really want to write things explicitly, instead of f prime t, you can also write here fx tau star. But of course that is cumbersome to write again and again, so we are using this short notation. So now we are going to define this function by a formula. So what is a general element in this quotient ring? Of course it is what we know quotient rings have. They are cosets of the ideal, principal ideal generated by fx. Cosets by what? By elements in this polynomial ring. So that means a general element will look like this. If you forget to write this outer parenthesis, then it's wrong, because this denotes the principal ideal generated by fx. In order to avoid confusion, some people use angular brackets. We, however, are not going to do that. We are going to follow Herstein. And then, so this is our input coming from the domain. Its output under the function is defined to be equal to, I can write g prime t here, but that will create unnecessary confusion. So although we have this notation to shorten things, we are going to write the things, at least here. So what I do, I apply tau star on this polynomial. So here I have written the image of gx under tau star, and the image of this thing under tau star star is the coset of this principal ideal generated by this. Now the first thing we want to make sure is that this tau star, the way we have defined, is actually a well-defined function. that has two things. First of all, for a given output, for a given input, the output that we see here must lie in the range or in the codomain, whatever you may wish to call this second set, this target's quotient ring. So we need to first of all see that this thing belongs to this set, and then we need to prove that for a given input there is only one output, uniqueness of the output. Once you show these two things, then you can say, okay, tau star star is well defined. So let's see that first of all. Note that gx tau star plus f prime t belongs to f prime t quotiented by f prime t. But how? Recall that tau star was an isomorphism of fx onto f prime t, right? So gx is coming from fx, so tau star gx, that means this comes from, this belongs to this, and that is why this is a coset of this principal ideal by an element coming from here. So this belongs to this set. It's nothing much. It's just a simple observation. And we are not even going to explicitly mention all these things, how this belongs to this set. It's almost obvious. But now we come to the main thing. We need to now show that this image is unique. Now, let g1x plus fx comma g2x plus fx belong to the domain quotient ring such that they are equal, that is, two equal inputs should give us equal outputs. So we now have to prove equality of outputs such that these two cosets are equal. Since a coset of whether you are in coset of a normal subgroup or of an ideal or of a subspace, since a coset generally has multiple representations, so if you are defining a function using cosets, then you really need to show uniqueness of image, because g1x and g2x as polynomials may be different, but still the cosets they give us may be identical. Okay, so we now have this. Then by the definition of equality, it just simply means that this difference belongs to the principal ideal generated by fx, which in turn means what? It means that this is a multiple of the polynomial fx in the polynomial ring fx. That is, this is equal to hx times fx for some hx belonging to fx. Okay, now we are going to apply the function tau star on both sides of this equation, which we can do because tau star has this as its domain, and all the things we see here, all the polynomials are coming from here. This implies g1x tau star minus g2x tau star equal to g1x minus g2x tau star. Why? Because tau star is a field isomorphism, so it will respect subtraction, which is equal to h of x fx tau star, and also tau star being a field isomorphism will respect multiplication also, so this is equal to h of x tau star times fx tau star, which in turn is equal to we can, if we want, write h prime t here, because that's what this I mean, this is just a name given to this, times f prime, this is just like that, f prime t. Note that this h prime t is an element in this polynomial ring, so that means this difference, this minus this, is now a multiple of f prime t in this polynomial ring. Thus, g1x tau star minus g2x tau star belongs to this principal ideal because of this thing. Which implies again by applying definition of equality of two cosets, g1x tau star plus the ideal generated by f prime t is equal to g2x tau star plus the ideal generated by f prime t. So these are what, this is the output of this input under the function tau star star, and this is the output of this input under the function tau star star. So that means when inputs are equal, outputs are equal. So tau star star gives us a unique image for every input. That is, in fact, let's just write one more step. g1x plus fx star star is equal to Hence this function is well defined. So that means it's a legitimate function, and now we can work with it. Now the first thing we will show is that this is a ring homomorphism, because it is a function between two quotient rings, but which are after all rings. So we can try to show that this is a ring homomorphism, and it turns out to be a ring homomorphism. So next, let us take two elements then from our domain quotient ring. What shall we take? Let us take gx plus fx, and say h we have already used here now. So let us take kx plus fx belonging to this. Now the usual stuff. First we will show that tau star star respects addition, and then it respects multiplication. We have gx plus fx. It becomes extremely confusing because so many brackets are involved. On this we are applying tau star star. So we perform the sum first, sum of these two cosets. I am not further distinguishing these two cosets by putting some other extra brackets, because we already have too many. So by the definition of sum of two cosets, this is equal to gx plus kx plus the ideal, and on this we apply tau star star. So by the definition of tau star star, this will be what? Gx plus kx, the element that is giving us the coset. On that element we apply our previous isomorphism tau star, and we replace this ideal with the ideal generated by f prime t. Now we use the fact that the previous isomorphism of course also respects addition. So and then by the definition of addition in the second quotient ring, our target quotient ring of the function tau star star, we can write something else in place of this. This is equal to the sum of these two cosets, gx tau star plus f prime t plus kx tau star plus f prime t. This is one coset, this is the other coset. But the first coset is just the tau star star image of this, and this coset is the tau star star image of this. So tau star star respects, let's just call it tau double star, respects addition. And next multiplication. Although these calculations are actually quite straightforward, but we should do this and see that we are not making any mistakes. In this jungle of symbols, do not lose track of what you are doing. Okay, if all the time you just you should be absolutely clear about what these symbols mean, what they represent. We are multiplying again two cosets of ideals, and on that product we are applying tau double star. So by the definition of coset multiplication, this is gx kx plus the ideal generated by fx, and on this we apply tau star star. So now we apply the definition of tau double star. Gx kx tau star plus f prime t. Tau star respects multiplication, so this is gx tau star times kx tau star plus the principal ideal generated by f prime t. Then by the definition of coset multiplication again, this is the product of gx tau star plus f prime t, this ideal, and this next ideal kx tau star plus f prime t. The first factor is the tau double star image of this ideal. And the second factor is the tau double star image of this ideal. So tau double star respects both addition and multiplication, and hence it's a ring homomorphism. Thus, or this shows that this is a, need not mention ring homomorphism specifically because we are dealing with rings and fields. So what else do we need to show? We have shown that tau star star, tau double star is a well-defined ring homomorphism. To prove that it's an isomorphism of one ring onto another, we next have to prove that it's one-to-one and onto. Onto-ness is almost obvious. Let's just see that one first. Next, and note how everything actually depends on the fact that the previous isomorphism tau star is an isomorphism, and that fact that tau star is an isomorphism in turn depends on the fact that our original function tau is an isomorphism between the fields f and f prime. Next, let us consider any element, say p of pt plus f prime t belonging to the range ring. That means pt is coming from this second polynomial ring. Then pt belongs to f prime t. Now since tau star is a function from fx to f prime t, and it is onto, so we have pt equal to qx tau star for some qx belonging to fx. Ontoness of tau star just proves that there exists some such qx whose image under tau star is this polynomial pt. Then our original element coset becomes what now? qx tau star plus f prime t. So this now becomes the image of qx plus fx, this coset under tau double star by the definition of tau double star, where let us also mention that this actually belongs to our domain of tau double star. These technical lemmas or results admittedly are not very interesting. They are rather dull and boring, but they will lead us to interesting things. So they are necessary. Where this belongs to fx by, it's better not to write the notation for a quotient ring like this, one part here, another part here. I'm just simply doing it here for lack of space, but you try to do it unbroken. This shows that tau double star is onto. Okay, so it's an onto ring homomorphism. So the only thing now left for us to show is that it is also one-to-one, and that we will show by assuming considering any element in the kernel of tau double star and showing that that should be equal to the zero element of the domain ring, that is this. Finally, let Rx plus ideal generated by fx be any element in the kernel of tau double star, then its tau double star image should be the zero element of the second quotient ring, and the zero element of the second quotient ring is what? the ideal generated by f prime t. That is the ideal which is giving us the second quotient ring. That is the zero element. That should be equal to the tau double star image of this. And this is equal to, by the definition of tau double star, this is the tau star image of Rx plus this principal ideal. Okay, so that means what? This coset equals this coset. Now cosets are equivalence classes, so two cosets are either identical or disjoint, and from properties of cosets this implies that Rx tau star should belong to the principal ideal generated by f prime t, which again then has its own meaning. Thus, this is a multiple of the polynomial f prime t in the polynomial ring f prime t. Thus, Rx tau star is equal to St times f prime t for some polynomial St belonging to f prime t. Now we again use the fact that tau star is this previous isomorphism is an isomorphism, so it's onto. Since you may have noticed that whenever I am using the onto property, ontoness of tau star, I am mentioning the domain and range or codomain. That is because it will show us what we are going to write. That is, we have an element here, so it will have an inverse image or a pre-image here under tau star because it is onto. S of t is equal to, say, write ux tau star for some ux here, that is the pre-image, one pre-image or inverse image. We thus have, so with this new information we go back to this equation. Rx tau star is equal to St f prime t. Now St is ux tau star and f prime t already is fx tau star, because that is the meaning of f prime t. Now you again use the fact that tau star is an isomorphism, so it respects multiplication, to write this final thing as the tau star image of this product. And finally, now it is time for us to use the fact that tau star is onto because it's an isomorphism. Since this is 1 to 1. Onto we have already used. 1 to 1 we finally have so we have what? The images are equal, that means the inputs, the original elements should also be equal. We have Rx equal to Ux Fx. Now what does this imply? This implies that Rx belongs to the principal ideal generated by fx in the polynomial ring fx. That is because this ux is coming from fx. Hence, the original element that is this coset, which we consider to be any element in the kernel of tau double star, has turned out to be the zero element of our domain quotient ring, and that's what we wanted to show. Thus, the kernel of this is the kernel of this, is the zero ideal in this quotient ring. And its only zero element is this ideal. This is the zero ideal, and that is why tau double star itself is 1 to 1. And hence is 1 to 1 or injective. So we have proved that tau double star is an isomorphism of our first quotient ring onto the second quotient ring. Let's write that down. We have thus proved that this is an isomorphism of our first quotient ring onto the second quotient ring. But that is not all. Recall that in the statement of the lemma we had to prove some properties that this tau double star satisfies. One of them looks like that thing that if you apply tau double star on any field element alpha, then you get alpha prime. So we are going to show that first. Next, for every alpha belonging to F, alpha tau double star. But we need to properly interpret what alpha means here when we are applying tau double star to alpha. It is not just simply the field element alpha, because you see, we are applying tau double star to what type of things? Those things that are coming from here, that is, those things that are cosets of this principal ideal. So by alpha, what we really mean here is alpha plus the coset given by that alpha. Now you may object, you may say that, okay, so if this is really what we want to write or what we have here, then what is our justification in writing alpha and treating alpha as simply alpha? That is because if you consider the map between the original field and this rather distant thing, this quotient ring, which is obtained in two steps. First you go from the field to the polynomial ring, and then from the polynomial ring you make things collapse and you form this quotient ring. If you consider this association where alpha is mapped onto this coset, then you get an embedding of F into this ring. What that means is that you get an isomorphism, a ring isomorphism of F into this, so that F as a, there is a copy of F, an isomorphic copy of F which is identical to F as far as fields go inside of this, and that in that isomorphic copy the image of alpha looks like this. And if one really applies the addition and multiplication of this quotient ring on this type of elements, one will see that these elements form a subring of this, which is itself a field, and that field is isomorphic to F. So because of this isomorphism between these things and F here, we can say that F itself lies inside of this. So that is how we are justified in writing alpha, and we can switch between these two things, whether we want to interpret this as a field element or really as a coset like this. Actually it does not matter. It does not matter, but we have to still keep in mind that we are actually applying tau double star on elements from here. So in that sense we have alpha here. Anyway, so applying the definition of tau double star, now what do we get? The image of alpha on tau star plus the principal ideal generated by F prime t. And here we are going to use lemma 533 because we already have seen that this thing gives us alpha prime. So if you want, beside this step you can write by lemma 533. I am of course not writing, I don't have space here. And again, by that identification, whatever identification you have, that is F is embedded in a very natural way using this identification, of course, inside this first quotient ring. In a similar, exactly similar manner, F prime is also embedded in this second quotient ring by an identification which identifies this coset with this field element. That's how you get alpha tau double star equal to alpha prime for every alpha belonging to F. So the first relation has been shown. And the second relation is of course easier than this. There we don't need any identification. Also, so this is one thing. Now if this particular coset is considered and on this we apply tau double star, then by the definition of this function, this is tau star plus principal ideal generated by f prime t, which is equal to, now you apply the definition of tau star itself on this polynomial x. What does tau star do? It replaces the given polynomial, I mean the indeterminate x, with t, and all the coefficients with their images under that original isomorphism tau. So you have to be a little careful here. Note that it is tempting to just simply write t here. We are writing, we see x in its place, we write t, and that's just it. But there is something else hiding here, which is that the coefficient of x actually is 1. Okay. That thing, although we do not normally write, but it is there. And so by the definition of tau star, we should have 1 prime here times t. Now what is 1 prime? You see, 1 is the multiplicative identity in the field F, and 1 prime by its definition is the image of 1 under that original isomorphism tau. However, because tau is a field isomorphism, this 1 tau, or which we are calling 1 prime, actually has to be the multiplicative identity in the field f prime. Okay. And that is why here also we do not write that 1 prime. Like normally we do not write. For example, if you write x plus x square, say this is your ordinary polynomial with real coefficients, you do not normally write 1, but it is there. So now 1 prime is the multiplicative identity in this field f prime, so we are not going to write it. And we have this. So that just completes everything, and now the proof is over. We have shown that that particular tau double star is an isomorphism of the first quotient ring onto the second quotient ring, which has these properties. With this, now we can move forward and prove ultimately that two splitting fields are isomorphic for the same polynomial, which becomes the identity function on the underlying field f if we restrict it to f. That, however, I mean, we will do other things in the next video. So with that, I end things here itself. If you want to comment on these things, you can use the comment section below, or you can mail me. My address will be there in the description. And today is what? Today is Tuesday. So that means the next upload is on Friday. So we have, again, in our cycle, we have gone through what? Group theory, vector spaces, and field theory we have done today. So this coming Friday, let's do calculus once more, and then we will go to other things. So that's just it. So I wrap up here itself. So see you on Friday. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.